what we learned, there was a word problem there involving creating a box out of a piece of paper or a piece of metal or whatever material we used. But essentially what we learned on Thursday of last week is that there is a way to kind of bypass all of the algebra and connect the features of a graph of a polynomial function to the factors of the polynomial function. And essentially what it boils down to is that the zeros of the function, which means graphically the x-intercepts of the function, are the zeros of all of the factors. So, for example, if you've determined that you have a polynomial function with the following x-intercepts, -2, 3, 0, and 5/3, then if -2 is an x-intercept of the graph of the polynomial function, what that means is that x equals -2 is a zero of a factor, and that means that it has to contain the factor. The polynomial function must contain the factor of x plus 2. If 3 is a zero or an x-intercept of the entire function, then 3 must be a zero of one of the factors of the function, which means that x minus 3 is a factor, and on we go. If 0 is a zero, you got to really think about what I'm saying there. The number 0 is a zero of the polynomial, which means when you put 0 in for x in the polynomial, you get 0 for y, so it's an x-intercept. Then x is a factor, because this 0 is a zero of this factor. In other words, this 0 makes this factor equal to 0. These three x-intercepts or zeros are what we would call integral zeros, because they're integers. And if you have an integral 0, then you're going to have a factor of the form x minus a. All of these factors, in other words, everybody, and this is going to be important for today, the coefficient of the x in each of these factors that gives an integral 0, an integer, the coefficient of x will be 1. This is what we would call a rational 0, and I've never liked that language because you would be told that that's a rational 0 because 5/3 is a rational number. But -2 is a rational number. 3 is because they can be written as fractions. However, when we talk about polynomials, the concept of a rational 0 means that it has to be written as a fraction in lowest terms. It cannot be written as an integer. Okay? And connecting these integral zeros to the linear factors is easy. It's probably the case that you don't even really think about what you're doing. You just go, well, if it's -3, it's x plus 3. If it's -8, it's x plus 8, etc. This requires a little more thought. And in this particular case, it must be 3x minus 5 to give the 0 of 5/3, because when you take 3x minus 5 and set it equal to 0 and solve it, you get x equals 5/3. I don't know what to tell you here. You need to know how to connect that factor to that 0 and vice versa. You know, I mean, I think it's pretty clear that when you have a positive 0, you're dealing with a negative number in the binomial, the negative in front of the constant term. The advice I've given people in the past is you look at that 0 of 5/3, and I would say, I think everybody here knows that that means it's going to be either 3x minus 5 or 5x minus 3. You know that, right? You know those two numbers are associated with the linear factor, and you know it has to be minus. So then the question becomes, if you set this equal to 0 and solve it, will you get 5/3? And since the answer is no, that's telling you that it's 3x minus 5. One, final comment here, and I mentioned this on Thursday. These rational zeros, which produce a factor that's not x minus a, but is a factor like bx minus c or something, these rational zeros will appear at most twice in any polynomial. You'll never be expected to analyze a polynomial function if there are 3 of those, but you will be if there's 2. So all that being said, does anybody have any questions from any of the assigned problems from Thursday? I'm really more concerned with this whole idea that I was talking about here, that you could use your graphing calculator to factor this. And by the way, you're not limited to looking at x-intercepts, right? You can look at the table. But again, the table is not going to throw out to you with a red flag numbers like 5/3. You're not going to know to set up your table to see a 0 like that. You're going to set it up to see all of the integral ones, and then hopefully you can piece it together with the x-intercepts for the remaining factors. So there are no questions at all? Yeah, go ahead. 5C, certainly. And again, the goal here, Marcel, is that we want to be able to factor this polynomial function using x-intercepts and features that we can see on the graphing calculator, like the tabular values for different values of x. And in my mind, I think most of you would agree and understand what I'm about to say. Sometimes determining the x-intercepts and getting the right zoom settings can be messy. So I generally go to my table first to find zeros that are integral. So, and that's what I'm going to do. I'm going to enter 2x cubed, and this is just how I enter it. Minus 9x squared minus 20x plus 12. Looks okay, double check everything. And I'm going to set up my table. I don't know what kind of state my table is in right now. I'm going to set it up to start at 0 and go up by 1. And then I can scroll up and down to see integral zeros. I see -2 is a 0. So right away I know that one of the factors is x plus 2. And this isn't a written response. I'm not explaining that. If it were a written response, I would write down since p of -2 equals 0, x plus 2 is a factor. It's looking like if I continue going in that negative direction, the value of y just keeps exploding in a negative direction. I don't suspect it's going to come back to 0. So I'm going to scroll down. It's increasing. Well, oh, there's one, 6. I mean, maybe what's called for here is patience, right? Like I was scrolling and just about ready to say, what, I must have done something wrong because I'm not seeing another one. So I see that 6 is a 0, and that tells me that x minus 6 is a factor. Now, I don't need to look at the graph to complete this question, because since this is a degree 3 polynomial, it has to, if it has 2 factors that are linear, meaning 2 factors that have a degree each of 1, and I have to multiply together those 2 factors with whatever else is there to get a degree 3, there must be a third factor. And the third factor must contain a 2x, because I have to multiply these 3 linear factors together to get the polynomial. And going back to the first day of this unit, when you multiply the highest degree term from each factor, you have to get the highest degree term of the polynomial. So if we already have x times x and we want to get 2x cubed, it has to be another 2x. Does that make sense? Okay, we've also learned, and this was back on day one, that when you multiply the constant term in each factor, you have to get the constant term in the polynomial. So 2 times negative 6 is negative 12. I need to put a number in that final blank that multiplies by negative 12 to give positive 12, so it would be plus 1. Now, if you weren't going to take that approach, and you cannot take that approach if you have two more factors that are like that. Right? If you have two factors that give rational zeros, you can't just figure them out by looking at it. Then you would have to go to your graphing calculator, and Zoom standard is not necessarily the way to go. In my mind, I already know, I'm imagining here, Marcel and everybody, that I don't know what this third factor is. I already know there's an x-intercept at 6 and an x-intercept at negative 2. Zoom standard takes me from negative 10 to 10. And I don't suspect, we already know the answer, but I don't suspect you're going to have an x-intercept past 6 or negative 6. So I would probably set up my window settings manually and go from negative 6 to 6. And since the y-intercept is 12, I can see the y-intercept is 12, I would probably scale things vertically to go from maybe negative 20 to 20 as a starting point. We can reevaluate that decision later. But again, graphs of polynomial functions tend to be quite steep. That's not bad. So I can see my 6, I can see my negative 2, and now I can see my x-intercept that I'm missing. If I go to my calculate menu and choose 0 and scroll to the left of it, which is there, hit enter, scroll to the right, it's here. So you end up with this. Now, I guess I'll show you another way to get the factor. If you know that the 0 is 1/2, we've just discovered the x-intercept is 1/2, correct? And I treat this like an x minus a thing, that would mean I could say that there's a factor of x minus 1/2 equals 0. And that's technically true. But we don't like fractions. So what can I do to this little equation I've created to get rid of that 2? Well, I can multiply both sides of this equation by 2. And when I multiply 2 by x, I get 2x. When I multiply 2 by negative 1/2, I get minus 1. 2 times 0 is still 0. So there's my factor of 2x minus 1. Is that okay? All right. Any other questions before we get started today? Arden? Sorry? Okay. So what this first sentence is saying is somebody did what we just did. And if we want to determine where p of x equals 0, think about this. If we want to determine where p of x equals 0 by looking at the graph of y equals p of x, we have two things going on here. We have this idea that we're looking at this graph, and we have this equation that we're trying to solve. But the p of x is the same for both. So really what we're looking at here is y equals 0. And y equals 0 is the textbook definition of an x-intercept. So the solutions to p of x equals 0 will be the x-intercepts of the graph of y equals p of x, which is exactly what we just did with Marcel's question. I mean, we didn't do it as an equation, but if you look at the resulting function that we had with Marcel's question, we had this for a polynomial function. But if I said to you, solve this equation, you're simply going to tell me the zeros of all of the factors. Okay? All right, let's move on. Just a couple of announcements here to make sure you're on the same page as me. Well, literally and figuratively, we're looking at page 20, but the assignment that I gave you in seminar this morning is due Thursday. I will take it in Friday. Okay, I mentioned this morning, but some of you may not have heard the message as we were coming in. I'll take it Friday, but if I take yours in Friday, you will not get it back before the exam, which is Monday. If you hand it in Thursday, you'll get it back Friday. So you'll be able to look at it before the exam. The exam is Monday. Monday is not always an ideal time for an exam, but I think it is ideal in this case because Monday is our seminar day again. Tuesday, Wednesday, Thursday, Friday, Monday is our seminar day again. So we will start the exam in the seminar. So you'll come in. We'll maybe have 3 or 4 minutes before we get started because there might be the odd question that people want an answer to quickly. But then we'll start, and that way you'll have lots of time. And even though it's a Monday, and even though you will have prepared, I hope, you still have that extra time. Okay. That's it. Yep, those were the little announcements. So what we are looking at today is really connected to Arden's question. We're going to be quickly looking at solving polynomial functions. And it's something that I kind of think, well, we should already know how to do, but we haven't officially, formally studied it. So we're going to be looking at how you solve a polynomial equation. And just think for a second about the fact that you know how to solve a quadratic equation. The quadratic equation is a polynomial function. So however you solve a quadratic equation, that's how you would solve a cubic equation or a quartic or a quintic, etc. Except we don't use a cubic formula like a quadratic formula. You know, the x equals negative b plus or minus the square root of b squared minus 4ac all over 2a. We don't use that for cubic or quartic or quintic. They exist, but they are a nightmare. I'll maybe show one to you later. And then we're going to be looking at really what Arden and I were just talking about, the relationship between x-intercepts of a polynomial function and the zeros of a polynomial function with an added layer to it today that is something called multiplicity. And on Thursday's assignment, in question 5, there were a couple problems, I think A and J, that I said don't do, right? Yeah. That's because they dealt with something called multiplicity that you were not aware of until after today's lesson. And this is the big part of today's lesson, is multiplicity and graphs of polynomial functions. But to begin with, how do we solve this polynomial equation? Well, first of all, I want you to understand something. That I could have given you a polynomial function and said solve the following. I could have given you this expression that I'm going to highlight. I could have given you this in expanded form and said solve it. Okay, we'll come back to that idea in a second. But now look at the equation that I've highlighted here. The product of those factors has to be 0. That's the equation you're asked to solve. Well, if this were a quadratic equation, and the quadratic equation in factored form looked like that, and it isn't, and it doesn't, but if it were, you'd simply look at it and you'd say, well, x equals 4, right? And your reasoning would be that if x minus 4 equals 0, which leads you to x equals 4, if this is equal to 0, then it doesn't matter what x plus 2 is equal to because it's being multiplied by x minus 4. So if x minus 4 is 0 and you're multiplying it by everything else, then the whole thing is 0 and the equation is true. Well, that logic shouldn't matter or shouldn't be affected by how many factors there are. You know, if there were 3 factors, then if any one of those 3 factors is 0, then the whole thing will be 0 because factors are items that are multiplied together. So the bottom line here is, to solve this polynomial equation, you simply go through the motions and you say, well, 2x minus 1 equals 0, and that will lead you to an answer. You say x plus 3 is equal to 0, And that will lead you to an answer. And you say x plus 2 equals 0. And that will lead you to an answer. So x would be negative 2. X would be negative 3. X is equal to 1 over 2, and it's positive. And of course, we've already said x equals negative, or x equals positive 4. I hope you understand. I hope you're catching my drift here, and I hope you also understand that this is something you already knew. We're just officially extending it beyond two factors. And going back to this statement, that means since we spent the first 2 days of the unit, well, the second and the third day of the unit, learning how to factor polynomials, then I should be able to give you a polynomial equation in expanded form and say, factor it and solve it. Just like if I gave you this polynomial equation that's quadratic, you would say, oh, well, okay, I factor it. It factors into x minus 4, x plus 2. The solutions are x equals 4 and x equals negative 2. Well, if it were cubic, you would factor it. If it were quartic, you would factor it. The difference, at the risk of being too repetitive, is that you have to use the remainder theorem and synthetic division or some other method to come up with all of the factors. It's not just done in your head. I don't think for too many people it would be. One final question about this idea. What is the relationship between the solutions of this equation? So when we talk about the roots of an equation, roots or solutions, we're talking about this thing. And the zeros or x-intercepts of the corresponding polynomial function, when we talk about the zeros or x-intercepts, we are talking about the polynomial function. And I don't know if you have this typing mistake there, but do you see at the end of what we're looking at up here, it says equals 0? Does yours say equals 0? It doesn't. It shouldn't. The reason it says equals 0 up here is when I copied into Notebook, I did some copying and pasting, and I forgot to re-edit it. So what's the relationship between the zeros or x-intercepts of the function and the solutions or roots of the equation? Well, they're the same. We already know this, right? They're the same. In other words, if I gave you a polynomial equation where it's equal to 0 and I said solve it, you could just go to your graphing calculator and find the x-intercepts. But we've talked about that. I think this is the third time we've talked about it in this course, that x-intercepts of a function are equal to the solutions to the corresponding equation. So any questions with example 1? Okay, so now what we're going to do is do some sketching here, and it says use a graphing calculator, but that would be if you were working on this on your own. I have the functions loaded up on a graphing program that will make it easier to see, but you know, before we graph this, you should be able to look at this function and say that we have the following x-intercepts. You should have an x-intercept at -1, shouldn't you? Because there's a factor of x plus 1. You should have an x-intercept at 2 because we have a factor of x minus 2, and you should have an x-intercept at 3. So I'm not really sure we need to cheat and peek and look at the graph on our calculator. I'd like you to focus up here that we're going to have an x-intercept at 2, an x-intercept at 3, and an x-intercept at -1. And, everybody, this is an odd polynomial function, right? Because if we expand this out, we would get y, or f of x, equals x cubed plus a whole bunch of stuff, and then we would have plus 6. you give some thought to where I'm getting plus 6 from? It's the product of the constant terms of all of the factors. This thing that we learned on day 1 is important, especially today. And it's x to the 3 because we have x to the 1 times x to the 1 times x to the 1 for the 3 factors. So this is a degree 3 polynomial function with a positive leading coefficient, which means the right arm is up, and since it's an odd function, the left arm is down. There's only one way you can sketch that curve with these 3 x-intercepts, and it would be to come up through here, down through here, and then back up. So I don't really believe we need a graphing calculator or a graphing program to know that. And by the way, this would be at 6. You already have the skills right now to tell me all of the features of that polynomial function because it's in factored form. If we take a look at what my graphing program shows us, it looks like this. So we did not a bad job. There is a tendency, by the way, here, and I don't believe I did it, but there's a tendency when we take, I kind of did, when we take a look at this to assume that that 6 is the highest point. Okay, it may not be the highest point. In fact, you can see if I locate the 6 there, it goes a little bit above the 6 once it passes it. So it doesn't have to be the highest point. Anyway, that's what it looks like. And I don't think that's anything new. Let's take a look at this one now. We are asked to sketch what the graph of this looks like. Well, let's make a list of the x-intercepts. We're going to have x-intercepts at, well, we'll have one at negative 4 comma 0 because of the x plus 4. And you know, if this were a written response, you would really want to explain that. You would say, since a factor is x plus 4, the value of x that makes x plus 4 0 is negative 4, so that's an x-intercept. We're going to have another x-intercept at negative 1, and we're going to have a third x-intercept at 3. So I hope everybody is okay with connecting those x-intercepts with those 3 factors. And I hope everybody understands why this is different. Because this is a degree 4 polynomial, everybody. But it only has 3 x-intercepts. If I were to expand this out, it's going to be x plus 4 multiplied by x plus 1 multiplied by x minus 3 multiplied by x minus 3 because that x minus 3 is squared. So if I were to expand it out, remember when you expand a polynomial, all we really care about to analyze the graph is the first term and the last term. I'm going to have to multiply x by x by x by x 4 times. I don't know if I said 4 or not, but we're going to get x to the 4. So it's a degree 4 polynomial. Both arms will be up because it's positive x to the 4. So whatever we sketch has to be going, and don't draw this because I'm just going to erase it in a second. Whatever we sketch has to be pointing up on both sides. Because it's even, both arms are in the same direction. Because the leading coefficient is positive, the right arm is up. We're going to get all this filling, and then what we're going to have is the product of all of the constant terms, which is 4 times 1 times negative 3 times negative 3, which I believe is 36. So we're going to have plus 36. Of course, the 36 is the y-intercept, so it's going to have a y-intercept up here at 36. Let's put in our x-intercepts. We have an x-intercept at negative 1, negative 2, negative 3. We have one at negative 4. Please wait and put up your hands so I can see who's talking. What's the question? Yeah. I don't believe so. It's 4 times 1 is 4 times negative 3 times negative 3. Negative 3 times negative 3 is 9. 9 times 4 is 36. Okay. So we have an x-intercept at -4, we have an x-intercept at -1, and we have an x-intercept at +3. So when you sketch these, you don't have to be, Rembrandt. Just put ticks relatively evenly spaced, and that's good enough. So you don't know what to draw here because of that x minus 3 quantity squared. So let me show you what this is going to look like. It looks like that. The x-intercept at 3, which is where we had x minus 3 squared, the x-intercept there is just a touching x-intercept. There's a better word that we're going to use in a second. But what the polynomial graph looks like is it does come down, which means the left arm is up. It changes direction, goes through this x-intercept, goes through here, comes down, and then just touches and changes direction. And of course, this is verification that we've got a positive x-intercept and or y-intercept, which happens to be 36. So this is what it looks like. Now, if I were to put what I just drew side by side with this, it's not perfect, but the important features are the same. And I'm going to use some words now to describe things. I would say that these two x-intercepts are what I call clean x-intercepts. The graph goes cleanly through the x-axis. There's no funny business going on. Clean is the word I use. This x-intercept is called a tangent point. And it doesn't really have anything, well, it does, but in this course we don't need to worry about it. It doesn't have anything to do with trigonometry. The word tangent here means it just touches and glances off of it, and those of you in calculus right now know exactly what I'm talking about. And the reason it's tangent is because of this exponent here of 2. So whenever you see an exponent of 2, you're going to get a tangent, x-intercept. All right, what about if we have an exponent of 3? Well, again, let's take a minute and write out what the x-intercepts will be here. The x-intercepts will be the zeros of the factors, because when a factor is 0, you get 0 for y, and that's an x-intercept. So we will have an x-intercept at -1, and we will have an x-intercept at +3. If we were to expand this out, we would have to multiply the following. And you would get f of x or y is equal to x to the 4. This is also a degree 4 polynomial, so both arms must either be up or down. And since the leading coefficient is +1, that's a positive number, the right arm is up. So if it's even, both arms are in the same direction. Since it's a positive leading coefficient, the right arm is up. So if they're both in the same direction, both arms are up. We have an x-intercept at 3. And we have an x-intercept at -1. The question is, what does that 3 look like? Well, what does that degree of 3 look like? Now just pay careful attention to this because I think it might be helpful. When the degree on the factor is 1, like up here with x plus 4 in the previous question, it goes through cleanly. It's steering in a particular direction and it just travels cleanly without any real abrupt change. If it's degree 2, it travels towards the x-intercept but then changes its mind and goes up. If it's degree 3, it's going to travel towards the x-intercept, change its mind, and then change its mind again. And the result is we get this shape. It's not going cleanly through. There's some wobbliness to it. There's a kink in the graph. There's a twist in the graph. But it's like it's going up towards I'm talking about from here. It's going up towards that x-intercept, but it's steering away from it. It's kind of wanting to change direction. And then at the last minute, it says, you know what? I'm going to go through anyway. So it actually goes through, but it goes through with a twist or a kink. And from now on, you need to know that if you have an exponent or a degree of 3 on a factor, you will have that feature. So how can we draw this so that the graph starts up here, ends up here? Well, and it has to start up there and end up there because both arms are up. The graph has to come down through this cleanly, go up with a twist. Now, I'm perfectly aware that drawing this twist is something that I could look at your work and they all look a little different. Okay? Don't worry about your ability to draw it perfectly, but try to have it so that on one side it has a downward curve and on the other side it has kind of an upward curve. Okay? This point is called an inflection point. So the graph goes through the x-axis with an inflection, and this is clean. So what I hope you've picked up from these examples so far is that if the exponent on the factor is 1, the x-intercept is a clean x-intercept. If the exponent on the factor is 2, it's a tangent x-intercept. And if the exponent on the factor is 3, it's an inflection. With that in mind, let's see if we can graph D without using technology to see what it looks like. I know, oh, by the way, one last thing here. If I expand this out, I'm going to get my filler, but then I'm going to have minus 27 when I multiply all of the constant terms. So my y-intercept will be negative 27, and that makes sense with what I've drawn. The y-intercept is negative. Here it is. Whoops. Here it is. So if we were to expand this out, we would have y equals x minus 3 times x plus 4 times x plus 4 times x plus 4 times x times x. So we will have an x-intercept of 3. And because, everybody, the exponent on the corresponding factor is 1, this will be a clean x-intercept. Whatever we draw here goes through without any wrinkles or turns. We will have an x-intercept of 0 because we have a factor of x. But since that exponent is 2, whatever we draw, we need to draw a tangent x-intercept there. We also have a negative 4. Not perfect in there with my scale, but I'll clean it up a bit. Whatever. Since the exponent on the corresponding factor is 3, this will be an inflection point. This is a degree 6 polynomial. Look, you do not have to multiply out all of these to see it will be x to the 6. What you can do is simply add the exponents on the linear factors together. Right? If there's an x minus 3 and there's one of them, and then there's 3x plus 4s and there's 2 x's, you're going to have 6 factors in total. So it's degree 6, which means both arms are going to be, in this case, up. Because if you expand that out, and you don't have to write this every time, I think you should be able to look at that and see you're going to get x to the 6. The y-intercept will be 0. And the reason it will be 0 is the constant in each term gets multiplied to give that. So you're going to multiply negative 3 by 4 by 4 by 4 by 0 by 0 because this is really x plus 0. In other words, everybody, since we have a factor of x, every term will contain x. You won't have a constant term, which makes sense because the y-intercept has to be 0. So how do we draw this with both arms up, with an inflection point here, a tangent point there, and a clean passage there? It has to look like this. Wrinkle. Now it's got to change direction at some point to go back up to this x-intercept, but planning ahead, it's got to hit that x-intercept and change direction. And then it's going to change direction again so that it can go through here. And again, how much detail we've got right here is not important in terms of how low the graph goes or how high the graph goes. What's important is the x-intercepts and the shape of the graph at the x-intercepts. So it goes down a lot further between the 0 and the 3 than it does between the -4 and the 0. All right, let's summarize this and then burn through the remaining examples. The fact that we have factors with different exponents is called multiplicity. The multiplicity of a factor simply means the exponent that the factor has. That's all. So in this example that we just looked at, x minus 3 has a multiplicity of 1 because the exponent on it is 1. And that means the corresponding x-intercept is clean. X plus 4 has a multiplicity of 3 because 3 is the exponent on the x plus 4. And that's shape-wise called an inflection point. And the x has a multiplicity of 2 because x as a factor is raised to the 2, and that's tangent. There's nothing wrong with saying the x-intercept has a multiplicity as well. So looking at this graph, I could say that the factor of x plus 3 has a multiplicity, I could say the factor of x plus 4 has a multiplicity of 3, or I could say the x-intercept of -4 has a multiplicity of 3. So let's take a look at the top of the next page. And what I'm going to tell you right now is the shape around an x-intercept with a multiplicity of 2 is the same as the shape around an x-intercept with a multiplicity of 4 or 6 or 8 or 10. If the multiplicity is even, 0 happens to be even. -2 happens to be even. When I say the multiplicity is even, I'm talking about 2, 4, 6, etc. The graph will be tangent at that point. You know, it might be tangent above or below. When you're looking at a multiplicity of an odd number, but not 1, 1 happens to be odd, then this is what we call an inflection point. And of course, if the multiplicity is 1, it goes through the point. Cleanly. And this word clean is just something I've always used tangent because that's in the curriculum. It's a mathematical word. Inflection, that's a mathematical word. But we don't have one for the other one. And I think clean or cleanly kind of summarizes it. And I suspect if you wrote a diploma exam and you used that and you said that x-intercept is clean, I think the marker would probably go, oh, yeah, that makes sense if they've never used it before. So the goal now, and you need to understand you have to be able to do this without a graphing calculator because the questions can be designed in that way. The goal now is for you to be able to sketch these graphs without looking at a graphing calculator at all. So looking at this, we have an x-intercept of 1, an x-intercept of -3. So it's kind of good to plan ahead here. I see that the largest x-intercept in terms of the size of the number is -3. So I'm going to scale it that way so I can see negative 3. What do we have? We have an x-intercept at 1. We have an x-intercept at negative 2. We have an x-intercept at negative 3. This is not how you would answer a written response. But I would, with you here, just between us, call that tangent. Because it's x plus 3 squared. I would say that this is a clean x-intercept. And this is a clean x-intercept. If you expand this out, you're going to get y equals positive x to the 4. You would show a little bit of work on an exam if this were a written response. This means that you're going to have both arms up. Because an even degree means both arms are in the same direction. And a positive leading coefficient means the right arm is up, so both arms have to be up. How are we going to do this? Well, start on the left. You have to start above and go down. It's going to be tangent. It has to change direction to go cleanly through that x-intercept. And then it has to change direction again to go cleanly through that x-intercept, and this is what it looks like. The fact that there's only one way to draw this that has a negative y-intercept means if you were to multiply out all of the constant terms, you'd better get a negative. And negative 1 times 3 times 3, because there's 2 of them, times 2, would give you negative 18, so it makes sense. Questions with A? All right, B. We're going to have an x-intercept at negative 1, 3, and negative 2. Negative 1 because of the factor of x plus 1, 3 because of the factor of x minus 3, and negative 2 because of the factor of x plus 2. The 0 or x-intercept, whatever you would like to call it, of 3 will be clean because x minus 3 is to the 1. The 0 at negative 1 is going to be clean because it comes from the x plus 1. You know, I would say the only way you're going to make a mistake here is just not being careful. You have to be organized and careful. The x-intercept of negative 2 is going to be an inflection point because of the multiplicity of 3. If I expand this out, I'm going to get x to the 5, among other stuff, because I will have x times x times x times x times x for the x plus 2 quantity cubed. So both arms are in opposite directions, and if the leading coefficient is positive, the right arm is up. So we have to draw it so that the graph begins in quadrant 3 and ends in quadrant 1. Try to plan ahead. We don't have a lot of room. If you look up here, we don't have a lot of room to work with here with everything that's going on. It's got to come up and inflect as it goes through that first x-intercept and then change direction right away to go back down. So it's coming up, it's curving, and then it curves in the opposite direction. Then it changes direction to go down. Then it goes through cleanly. Should have a negative y-intercept rather, according to this. And if you multiply 1 by negative 3 by 2 by 2 by 2, which should be the product of all of the constant terms, you'll get negative 24. Are we good with that? So we have an x-intercept here of 5 over 2 with a multiplicity of 1, because it's 2x minus 5 to the 1. we have an x-intercept of 6 with a multiplicity of 3, and we have an x-intercept of negative 2 that arrow is not really necessary. You can see where these numbers are coming from. You have an x-intercept of 6 with a multiplicity of 3, and you have an x-intercept of negative 2 with a multiplicity of 1. I'm just summarizing the information in a slightly different way. So 5 over 2 is 2.5. Here's 1, 2, 3. Here is our x-intercept of 5 halves. And I can see right away I'm going to have to rethink how I've scaled things. Because I have an x-intercept of 6, I'm not going to reach 6 there. So I have to scale things to see my largest x-intercept. 1, 2, 3, 4, 5, 6. We have an x-intercept of 6, an x-intercept of 5 halves, an x-intercept of negative 1, negative 2. 5 halves is clean. 6 is inflected. Negative 2 is clean. But you see this little bit of business here, that negative 1. That means if you were to expand this out, you would have y is equal to negative 1 times 2x minus 5 times x minus 6 times x minus 6 times x minus 6 times x plus 2. And when you expand out the highest degree terms, that negative 1 is part of that effort. Negative 1 is the highest degree term in that factor of negative 1. And we're going to get negative x to the 5. Well, we're going to get actually negative 2x times x times x times x times x is 2x to the 5 times negative 1. You'll get negative 2x to the 5. You can also figure out the y-intercept by multiplying the constant term in each factor. So we talked about this on day 1. Something like a factor of negative 1 is both the highest degree term in that factor and the constant degree term in that factor. So when we multiply out all of those numbers, where was I? If I expand this out, if you look at the bottom of the screen, y equals negative 2x to the 5, which means since it's x to the 5, the arms have to be in opposite direction. Since it's negative 2x to the 5, the right arm has to be down, which forces the left arm up. So we have to end here and start here. So we have to go through this cleanly. We have to, anticipating what's going on, we have to go through this one cleanly, so we're going to change direction nice and smoothly. Then we have to change direction again at some point to come down towards this x-intercept, but we're going to leave ourselves room here so that we can curve to go through it with a kink or a twist or an inflection. And again, this would be negative 1080, 2160. I got 1080 stuck in my head. Negative 2160, right? Okay. So we skipped D. Did we skip C as well? Okay, let's do C. We will have an x-intercept of negative 5, negative 1, 2, 3, 4, 5. That will be clean. We will have an x-intercept of 1 that will be tangent because it's degree 2 for a multiplicity. An x-intercept of 2, 3 that will also be tangent. If we expand this out, we would get y equals positive x to the 5. Are we all okay with those statements? X-intercept at 1 and 3, both tangent. X-intercept at negative 5, that's clean. And if we expanded it out, it would be positive x to the 5. Positive x to the 5 means we need to end in quadrant 1 and start in quadrant 3. Well, it's going to go through clean. It has to change direction now so that it can be tangent here, and it has to be tangent here. So it's going to come down, be tangent, change direction, be tangent, and go back up. And that's what it looks like, other than the fact that I kind of missed my x-intercept here, but let's not critique my artwork. I think you guys get the idea, yeah? Do you understand that with D and E, is there an F, by the way? No. With D and E, and probably F, the difference is that -1 in front, which flips things upside down. Doesn't affect the x-intercepts, though. So if we take a look at D, if we expand this out, this would be -x⁴. Just give a moment's thought to where I'm getting -x⁴ from. Remember, it's x plus 3 times x minus 2 times x minus 2 times x plus 2, and then times the -1. That means both arms are down. We have to start in quadrant 3 and end in quadrant 4. We have an x-intercept of -3 that will be clean. We have an x-intercept of -2 that is also clean. And we have an x-intercept of +2, which is a tangent. The only way to draw this is to go up and, I shouldn't be so cavalier. The only way to draw this is to go up and down, and then it has to change direction so that it can be tangent to that point. And again, if you've drawn things properly, everything matches up. Your y-intercept will be negative, which is what it would be if you multiply the constant terms together. We started in quadrant 3, we ended in quadrant 4. It's internally consistent. You don't get any contradictions here. And F, well, I'll give you a minute to draw this. And then I'll do the same thing. Should be in agreement. You know, and again, the artistic nature to this, what a marker would be looking for is some kind of wobble at the inflection point. And they would be looking to see that, well, we don't have any clean ones, but if we did have a clean one, they'd be looking for a nice, not straight, because it's got to have some kind of curve to it, but a normal curve, not a wobbly one, not a changing of direction. And that's really it. Tomorrow what we're going to look at is taking this just a little bit further. Rather than just having a -1 in front, we can have other numbers as well. This practice is all about creating an equation by looking at the graph or drawing the graph by looking at the equation. And remember, it has to do with multiplicity. I hope that made sense. Was that okay today? All right. Give me a second to just do a couple of quick things at my computer, and I'll come around and I'll give you a hand.